All right. Hello, everyone. Welcome back to Math 162. This is our sixth meeting together in total, week 3, lecture 2. Just going to remind you of the due dates on the horizon, two of them today, 5.3 and 5.4. And then we will finish 5.5 and 5.6 today. We had very little from 5.5 to finish. That's why I said go ahead and, kind of act like the homework was due for the 15th, but even still, it's actually due on the 17th. 5.6, we won't spend nearly as much time on, although we will still spend a decent amount of time on it because the graphs are a little more complicated than the stuff from 5.5, but we'll talk about how we are going to do more from 5.5 than 5.6 moving forward. But let's not waste any time. We'll first show you that the little whiteboard notes and stuff that I like to use, and then we'll get back into the graph stuff.
Usual board notes pulled up in case we need to have any of them. Cosecants, reciprocal sine, et cetera, et cetera, et cetera. Tangent, sine over cosine, your SOHCAHTOA, your two extremely important triangles, your smart trig class to get sines, cosines, and tangents of angles bigger than 90. For your quadrantals, your unit circle, the points because sine is the y, cosine is the x, and tangent is the ratio of them. Now, we haven't been playing with this one too much for at least a few classes, but we're going to get into it today. We're going to use it a little more because once we get into the next section, we're going to be graphing tangents, cotangents, secants, and cosecants. So this first section is only sines and cosines. So as a reminder, we spent a long time developing all 17 of these points for the graph of the first wave of a sine wave with a period of 2 pi, or 360 degrees, an amplitude of 1, which is the maximum height to get to a peak or a valley, and with no phase shift at all. And then the 4 divisive points were 90, 180, 270, and 360. Because that's the period divided by 4 that you just keep adding over and over and over. But we said, don't do it that way, do it this way, 5-point method, where 0, 0, 0, the first, third, and fifth, the amplitudes, the second and the fourth, they might swap, they might go down and then up instead if the number paired with the amplitude was negative, and we saw examples of that. We saw that this is the general form to be able to identify your amplitudes, periods, and phase shifts, which you first have to do as all those numbers. I'm also realizing that I have a mistake written over here. And I know I did the examples as C over B, but I have B over C written there. Ooh, where's my eraser? There we go. I know I always did C over B as the example C right here, C over B. I just had it written incorrectly there. That's what happens when you're thinking, writing, and talking at 3 different speeds. There we go. So we said C over B is the phase shift. Remember to be careful that the sign is opposite of the direction of the shift. It's a common theme in math. A is the amplitude when you absolute value it. And then the period was 2 pi over B. This is something that a lot of people mess up, and it's probably the most important aspect. Well, they're all important. One detail miss gets the whole thing wrong. But a lot of people will just say the period's 2 pi no matter what. But if there's a number in front of the x, that is speeding the wave up, and it makes the period shorten. A faster wave has a shorter period. All right, so we did a whole bunch of different examples. We said once you get your shift, then you take your period and you divide it by 4 and you add it 4 times to get points, the x values of points 2 through 5. We went through the process of algebraically finding the y values. We also said that inherently for sine waves, 0 are the anchors in the middle, the amplitudes are the second and fourth, just being careful with the sign placement based on whether A was positive or negative. We showed what a couple different waves all on the same plane would look like, the blue being just a regular old, the black being a regular old sine wave, the blue being one with a doubled amplitude, the red one being one with a doubled speed. Okay. Then we switched to a cosine wave. This is where we left off. And we did not do the 17-point approach. We said it's very similar. It's going to have the same type of shape, just out of phase because of this relationship here. But we did go through and establish these 5 values and then just made a nice curly wave bending to and fro from there. So this is our basic template for a cosine wave. The zeros are on the second and fourth. The amplitude values are on the first, third, and fifth. Now the first and fifth will always match. The third one will be the opposite. So again, if you had a negative A value instead, what your wave would look like is this. The negatives would be first and fifth, and the positive would be the middle one. It just depends on whether the A is positive or negative. And you don't have to memorize all of that. You can just show all of the algebra and trig along the way. But it's nice to have shortcuts when you understand them. So our template for one wave of sine looks like a very traditional wave. The template for the cosine looks a little different, and it almost looks like you draw a V when you just have the points there and not the curve. But it does look like this, and we showed that if you just kept extending the cosine wave, that it ends up having the shape of a sine wave as if you extended it. They're the same thing, just out of phase. Cosine starts at 1 or -1, whereas sine starts at 0. And it's kind of fascinating because that simple idea right there, whether you start at 1 or start at 0, can change very, very complicated mathematical problems in severe ways. But we're not there. We are going to go to example 2? A, B, C, yes, example 2. Oh, but first, point out that y equals a cosine parentheses bx minus c has the same exact process for finding amplitude, shift, period. That does not look like shift. It looks like shid, shift, the thing that you would add to it as y equals sine of blah, 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 blah. All the details are the same. Same amplitude process, same period process, same shift factor process, same take the period divided by 4 to find what you add over and over and over process. It's just a matter of what the template looks like of one waveform. Now we're ready for example 2. Graph, one wave, let's go with y is equal to 2 cosine parentheses. I don't want to make this inside too messy, but I do want it to be a little messy. Let's go with (2x plus 8 pi). So first thing you want to do is write down what your a, b, and c are. The a is positive 2, because that's a positive 2. The b is also 2, because this is a 2, that's the b. And then the c, I'm actually going to call this negative 8 pi because this was a positive. I've said several times that if you're writing a different SIG in for that, that's okay as long as when you do the graph that you graph it correctly and it would be shifting it left, because that's a plus. It means it shifts left. Horizontal shifts are backwards. That's a concept from pre-calc 1. Why does that keep happening? Probably because I don't have enter hit enough. This is going to mess things up. That's that classic issue. Oh, word behaved. It usually doesn't like inserting a blank page after that. Okay, it usually shifts everything down. So we got our A's, B's, and C's, which means we can identify the fact that the amplitude is going to be 2. The period is going to be 2 pi over b, 2 pi over 2, which is pi. Then the shift, the phase shift, whatever you want to call it, it's called a phase shift in more complicated classes, is going to be the negative 8 pi, the c, over the b, which was also a 2, which is negative 4 pi, which means it's shifting left. We already established that. Because that's a plus, This is shifting it left. If it had been a minus, it would be shifting it right. And messing up that one minor detail will screw everything else up moving forward. So we need to first find the x values, which means we start with the shifting value. The first point should be negative 4 pi. X1 equals negative 4 pi. X1 equals negative 4 pi. Then x2, we take that negative 4 pi, and I did this out of order intentionally, and we add something. What do we add? Well, I didn't say what to add. The adding bit, we're supposed to add the period divided by 4. Period is pi, and we divide that by 4. Again, the adding value is the period divided by 4. Go back to your previous notes. If you're not taking notes, well, I think you know what I would say in response to that. Okay, so we're going to have to get an LCD. The LCD between 1 and 4 is 16. The first one's going to become 16. I think I just said, I'm trying to talk right and think at different speeds. Between 1 and 4, the LCD is 4. So your denominator is supposed to be a 4. For the first one, 1 goes into 4. 4 times 4 times 4 is 16. So that's negative 16 pi plus pi, both over 4, which is negative 15 pi over 4. The third x value, we'll take the previous one, negative 15 pi over 4, and we add that pi over 4 again. Negative 15 plus 1 is negative 14 pi over 4, which is also reduced to negative 7 pi over 4. Sorry, I had to write a little small there. Your fourth point, we take the last one. I'm actually going to take the non-reduced version just to save myself a step. I've discussed that previously. So negative 14 pi over 4, and then add the pi over 4, which is supposed to be in red. Negative 14 plus 1 is negative 13. So negative 13 pi over 4. That's our fourth value. Our fifth x value, take that negative 13 pi over 4 and add pi over 4 again. Negative 13 plus 1 is negative 12. That's negative 12 pi over 4, which reduces to negative 3 pi. Remember to check that this is correct, that you've done everything correct. If you take the period and add the shift value, you should end up at the end point. And negative 4 pi, that's the starting point. Add a single pi, does give you negative 3 pi. It is correct. So those are the x values, which means we can start forming our table of values that I like to write horizontally in a trig class. You could do it vertically for 5 points. That would be perfectly okay. So the x values were the first one, negative 4 pi. Second one was the negative 15 pi over 4. The third one was the negative 7 pi over 4. The next one, negative 13 pi over 4. And the next one was the negative 3 pi. Now, I will mention, I know what these y values are going to be based on the cosine pattern. So a reminder, I'll come back in a second. That table for cosines always goes the amplitude, positive and negatives on the first, third, and fifth. It's the second and fourth that have the zeros. So the second and fourth are always zeros. I will show the work for some of these after, but I want to show you how you can shortcut it based on patterns. I know these are zeros because it was a cosine. You have to pay attention. If you thought this was a sine, if you weren't paying attention, you'd put zeros on the first, third, and fifth, and it's wrong. Undo's being weird, sorry about that. It's the first, third, and fifth that'll have the amplitudes positive and negative. The first and the fifth should match, and because this was a positive 2, again with practice, I know that this would be a 2, and this would be a 2, and the middle has to be the negative 2. If this had been a negative 2 originally, all the signs would swap. So it would be negatives for first and fifth, and a positive in the middle. But let's actually establish this fully. So in orange, So the first one, y1, that will be, let's pull the original function up, 2 times the cosine of parentheses 2 times negative 4 pi, then a plus 8 pi, close that outer parentheses. 2 times negative 4 is negative 8, so this is 2 cosine of negative 8 pi plus 8 pi, and as always, that becomes 0. The cosine of 0, if you go back to your sheet stuff, and again, this is the stuff that you are allowed to write once you start a test, but you cannot have written down beforehand, don't you dare. So cosine of 0, cosine's the x-coordinate is 1. So this is 2 times 1, which is 2, confirmed. Now the last one's the same, so I'm going to go ahead and put that as a 2. The second and the fourth were always the same for it, no matter what, so let's show the first one. We'll assume the fourth one from there. So let's do y2 equals 2 cosine of 2 times negative 15 pi over 4 plus 8 pi. Open, open, close, close, good. Which is 2 times the cosine of the 2 and the 4 will reduce to a 1 and a 2. So that's negative 15 pi over 2 plus 8 pi, which you'll have to get an LCD on, which will be negative 15 pi over 2 plus 16 pi over 2, which is 2 times the cosine of negative 15 plus 16 is 1, so it's just pi over 2, which is what you always expect that input to turn into after the processing. Cosine of pi over 2, that's cosine of 90 degrees. At 90 degrees, the x value is 0, so this is 2 times 0, which is 0. Boom. Second and fourth, always the same. The other missing value is always opposite. This will be a negative 2. I'm going to leave you to try that one on your own. So confirm y3, y4, and y5 if you dare. I used some patterns and assumptions still, just because the interest of time. I think I've mentioned this, but these are time-consuming problems. Even with the shortcuts, they're fairly time-consuming. Getting the x values, you can't avoid this. You're gonna have to do the blue stuff. You cannot avoid this. You cannot avoid this. With pattern recognition, you can avoid the orange stuff, though. We're still not done. We got to graph the table of values. So this graph, the x values are in the negatives, so I actually need to make this a pretty negative heavy x-axis. And we got to go all the way to negative 4 pi. So let's go, this will be 2 pi, this will be 4 pi in terms of negatives, of course. Negative 3 pi would be here, which means negative pi is here. Now, I do that just for sense of scale. We do need these two labeled, so it's a really good idea to label those. But then we're also going to need to label these middle x values as well, the negative 15 pi over 4. And again, everything is squeezed in this area. So that's where the only section is going to be. I didn't make my y-axis as tall as I would like it either. So let me just go a little taller. That's better. All right, so the x values again were the negative 7 pi over 4 should be the middle one. I always like to do the middle ones so I can then split the differences, but doing this by hand. This is the negative 15 pi over 4, and this would be the negative 13 pi over 4. Again, the left one, these are all in order. Negative 4 pi, negative 15, negative 7, negative 13, negative 3, again, with all their denominators in place. So the graph will do in blue. At the negative 4 pi, we have a height of positive 2. So let's go 1, 2. Then we'll have heights of -2 as well. So let's go down equidistant. Now we're ready. All right, a height of +2 at 4 pi. So we're here. Then a height of 0 next. Then a height of -2 next. Then a height of 0. Then a height of 3 pi. Why did I say 3 pi? Excuse me. I was looking at that. A height of 2. 2, 0, -2, 0, 2. Again, it looks like a V. Do not do this. Do not connect this as a V. This is wrong, 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 wrong. Connect it in that nice wave-like pattern. So bend, bend, bend. There we go. Bend, bend. This left one, I kind of flattened out a little quick. Let me try that one more time. It wasn't awful. And if I grade these by hand, which I said I might, haven't decided yet, I'm not going to, oh, you did terrible with that one little hump, so it's a -500 points, right? No, absolutely not. That's not what this is about. What I'm saying, what I'm looking for if I looked at this by hand is, did you make your table of values? Did you have some type of algebra you had an arithmetic to get that table of values? Because if you just wrote those down, I'm going to question how you got those. Did you do this identification of amplitude, period, shift, adding number? And you know, you might be missing 1 or 2 of those details, but if you have a picture that looks relatively like this, good table of values, a well-labeled set of axes, then you'd get a 100 for that question. I mean, 5 points out of 5 points, 10 points out of 10 points, whatever it's worth. But if I see that you drew the wave, if I only ask for one wave and you drew it over here, if you did this, which was poorly drawn, something like that, still poorly drawn, I can do better. Undo, darn it. I can't do better, clearly. So if this wave was just over here, I would not give you full credit for that. I would say, well, you did a good job of getting the period right. You did a good job of doing the addition right under what you have. And you got the heights appropriate where they're located, but you didn't draw what I call the initial wave. So that would not be full credit done by hand. Now, again, in your homework, it's kind of drag and drop, fill in the blank type stuff, maybe even multiple choice style stuff every now and then. Like you have to select cosine wave, and then it just automatically gives you this shape. That doesn't even make you think. I don't like that, which is why I said I'm considering kind of a handwritten portion that's mandatory for this test, specifically for this. But I can't give you 10 of these. It's going to be like 2, and that's it. One simpler one, and then one more difficult one. So if I were to give you 2 of these on a test and you had to do them all by hand, one would be in the ballpark of something like either A or B. So either something like sine of just, and then a number with the X, or just a number and then plus or minus with that. And then I'd give you one that's a little hairier, which has everything accounted for, amplitude, an A, a B, a C, all that stuff. But I would not give you 5 that look like this. That would be out of the question. That would be the whole test. So once again, know your waveforms. Yes, it is true that this thing continues forever and ever. This is much better. And it goes forever, ever, 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 ever in each direction. But in terms of by hand, I'm a big fan of the one waveform. Especially because when you do the forever and ever and ever, you don't have to have the difference of the sine wave versus the cosine wave memorized. But that little difference is helpful. So that's where we're going to leave off for 5.5. We have finished 5.5, which means we're ready for 5.6. Let's do this. New file. Close that one. I don't think I had anything typed up for this. Just double checking. Good. So 5.6, graphs of other Trig center, bigger. bigger. There we go. Take off that. Enter. Boom. Lots of space, lots of space, lots of space, lots of space. So now, what do I mean by other trig functions? I mean not just sine and cosine, tangent, cotangent, secant, and cosecant. So secant of x, not uppercase it, thank you. Secant of x, cosecant of x have the same a, b, and c as sine. Cosine waves. Well as period, shift, add, all that stuff. The A you identify is the same, but it's not quite an amplitude anymore. It's going to be kind of weird. Even though the A is still the same and it's an important identifier, it's no longer what I would traditionally call an amplitude, as we're going to see. To graph secant and cosecant, we'll need to graph their respective reciprocal functions and draw parabola-like shapes from the peaks or valleys. I'm going to explain why after the instructions. So to actually graph a secant or a cosecant, you have to graph the sine or the cosine first and then do more things. So it's like there's an implicit problem inside of these. So you'll draw, if you have a cosecant, you'll draw a sine wave. If you have a secant, you'll draw a cosine wave. And you would do that with the same A, B, C, period, shift, adding the period divided by 4 over and over and over, all that stuff. Once you get that wave, what you will then do is draw parabola-like shapes. I'm not saying parabolas, I'm saying parabola-like. So when I say parabola-like, we know a parabola does this, but parabolas go, and I'm doing this exaggerated, they go left and up forever, or down and left and down and right forever. That's a real parabola. Oops, too much. What we're going to end up drawing is a parabola-like thing that is stuck between two asymptotes, as I'm about to explain. This is what I mean by parabola-like. It kind of looks like a parabola, but instead of going left and right forever, it's actually sandwiched between two things. It can't move right past that. It can't move left past that in the instance of trying to look like a parabola. We had issues like this pop up when we were graphing rational equations back in Math 161 or Pre-Calc 1, wherever you had it. So the idea of an asymptote should be in your wheelhouse. Always go one too far. Okay. So since I want to actually draw this, 1 divided by 0 is equal to undefined, something you better know. If you're getting it backwards, there's no more time to get this backwards. 0 divided by anything is 0. Anything divided by 0 is undefined. You are not allowed to ever get that wrong again. All right, so since 1 divided by 0 is undefined, anywhere a sine or cosine was 0, there will be vertical asymptotes, cosecant, secant. And this is because they're reciprocals. There we go. So if the sine is 0, that means the cosecant is 1 over 0, which is undefined. So anywhere on a graph, your function was 0. If you're supposed to be actually graphing a reciprocal function, that means the real thing you're drawing, you've got to do big vertical lines, dotted lines generally, to represent a vertical asymptote, to represent that it's going to either infinity or negative infinity. So, due to this, Cosecant of X has vertical asymptotes of n pi. What this means is n is an integer. It's a 3 or a -7 or even a 0, a 1, a 2, a 3, a 4, a 5. I'm saying that cosecant has vertical asymptotes at every multiple of pi. That's what n pi means. Because sine at every multiple of pi is equal to 0. Here's the proof of that. Very easy proof. We're going to the unit circle and the quadrantals. Wherever sine is 0, cosecant will have vertical asymptotes. Sine is the y value, so we're looking for y coordinates that are 0. Here is a y coordinate that's 0. Here is a y coordinate that's 0. And remember, you can keep going around this thing as many times as you like. So it happens at 0, then it happens at pi, then it happens at 2 pi, then 3 pi, then 4 pi, 5 pi, 6 pi, 7 pi, 8 pi. Every multiple of pi. It works if you go backwards as well. At 0, then at negative pi, negative 2 pi, negative 3 pi, negative 4 pi, negative 5 pi. Those y coordinates are always 0. So it means sine is 0, which means the reciprocal function cosecant is undefined. So that explains all of that stuff. So a cosecant graph, just a standard cosecant graph without any A's, B's, and C's mucking it up, muddying it up, whatever, would have asymptotes at 0 pi, 1 pi, 2 pi, 3 pi, negative 2 pi, negative 3 pi, anything like that. And secant of X has vertical asymptotes, VAs, I'm just abbreviating now, of, and this one's a little weirder, pi over 2 plus n pi. So n is the integers. Integers are your -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, 5, extending forever and ever. So what I'm saying here is that your secant is going to have those dotted vertical lines every multiple of pi over 2 and adding a pi. That's what this says. Why is this? Okay, let's go back to the cheat sheet, unit circle. So now we're talking about secant, which means we're focusing on cosine. Cosine takes the x coordinate, which means secant flips the x coordinate. So if we're looking for vertical asymptotes of secant, that means we're trying to figure out where cosine is 0 because secant would then be dividing by 0. So we're looking for x coordinates of 0. X coordinates of 0 are here and here at 90 and 270. 90 degrees, that's pi over 2. But the next one occurs a single pi later. If you add 180 degrees, which is pi, to 90, you get 270. So it's not adding in pi over 2, which is what some people might think it is. The next one happens at 3 pi over 2, because that's adding another pi. Then the next one happens at 5 pi over 2. Then 7 pi over 2. Those are when your cosine is 0, which is when your secant is undefined. And to go from the first to the second to the third to the fifth, you're just adding pi. You would add pi to get to the 3 pi over 2. You would add pi to get to 5 pi over 2, because pi is 2 pi over 2. 3 plus 2 is 5. 5 plus 2 is 7. 7 plus 2 pi over 2 is 9 pi over 2. So that's the rationalization. There we go. As to why it's this. You start at the 90-degree angle, and then you add multiples of 180 degrees. That's what this says. This says we're starting at the 90-degree angle, and we're adding multiples. The n means multiples of 180 degrees. That's what it would look like in terms of degrees. But as you've seen so far, all graphing is done in radians traditionally. We haven't even gotten to the picture yet. All right, so what does this look like? Here's the process for, I want red there, okay. So for y equals, we're going to do cosecant first. Yeah, cosecant, because that's the flip of sine. For the graph of cosecant of x, what we first do is graph y equals sine of x. So in blue, I'll graph y equals sine of x. Now I'm only going to do the one wave. So from 0 to 2 pi. So let's put 2 pi here, puts pi here, pi over 2 here, 3 pi over 2 here. Heights of 1. I don't want to make it that high, actually. I need to, let me extend this a little more, and then let's put a 1 about here and about here. So in blue, this is our sine. So it starts at 0, third is 0, fifth is 0, the second point's the 1, the fourth point is the -1. Nice wave, nice wave, nice wave, nice wave. XY axis. There we go. So to graph these, you'll need to graph their reciprocal function. So cosecant and sine are reciprocal. So I graph that first. Then what you do is you draw parabola-like shapes from the peaks or valleys. And then you'll have asymptotes on every multiple of n pi. So the vertical asymptotes are wherever this original thing was 0. So there would be an asymptote, just a little bit, here, because the graph was 0 here, which means the reciprocal graph is undefined there. The graph is also 0 at pi, which means it's the reciprocal graph is undefined at pi. And then the graph is 0 at 2 pi, which means the reciprocal graph, the one we really want, is undefined at 2 pi. Then what we do is we draw parabola-like shapes from the peaks or valleys. How do you know whether you go up or down? Just don't go against it. So you want to go opposite. So here's a peak, which means we're supposed to draw up. Here's a valley, which means we're supposed to draw down. This is wrong. If I do this, it kind of looks like it's going along with the wave, but that is not true. If you went and calculated a ton of values, you could prove that. We don't have that kind of time though. This is what it's supposed to be. You draw parabola-like shapes, but remember, eventually you're going to be squeezing towards that asymptote. I'm going to move where I wrote y equals cosecant of x. Where do I want to put it? I'll put it just below. Here we go. Now that's this first one. There's a valley over here, so we do the same thing, but since it's a valley, we point it down. And again, asymptoting. There we are. So the black ink is the graph of cosecant. The blue ink was the graph of sine. This was just one waveform of it, and the actual cosecant doesn't look like a wave. It doesn't look like a wave at all. Sines and cosines are our waves. The rest of the trig functions aren't waves. They still have wave-like behavior, but not when you graph them. But that doesn't mean that their reciprocal functions are unimportant. They are absolutely important. Lots and lots and lots of stuff that we can take from them. All right, so there's our cosecant graph. Next up, we need to do the secant graph. But I want to make a little memo here. Because cosecant of x is not undefined at x equals 0, we want to shift the graph. We want to actually graph between the vertical asymptotes. So we actually start a little to the left. How far left exactly? Negative pi over 2, because negative pi over 2 is the closest negative x coordinate that would be undefined for, I said cosecant, I was supposed to say secant. Jesus, sorry about that. Because secant, erase. Why aren't you erasing? Erase. Thank you. There we go. Because secant. That's what happens when you're looking at words over here and writing things. Because secant is not undefined at 0. Because remember, secant has vertical asymptotes at multiples of pi over 2 and adding pi. So negative pi over 2, positive pi over 2, 3 pi over 2, 5 pi over 2. If you do the graph starting at 0 and going to 2 pi, which is exactly how you would do it for a cosine, it makes the secant graph look really wacky. So what someone decided a long time ago to do is, they said, I want it to look more similar to the cosecant graph, so let's just shift where we start. And that's what's going on here. So we shift it a little left, and we start it as negative pi over 2, because that's the first closest negative value that leads to a vertical asymptote. So the period is 2 pi, which means the fifth point, if you add 2 pi to that, what you end up getting is 3 pi over 2. So we start at negative pi over 2, then 0, pi over 2, pi, and 3 pi over 2. Those will be our 5 points for the secant graph. All right, so again, similar shape. They might not point up and down in the same order. Hint, wink, nudge. They might. Hint, wink, nudge. I'm not telling you. Let's see what happens. All right. Maybe that's what it is for tangent and cotangent if it's not this time. So we're going to start a little to the left. I want to try and go about the same vertical distance, so these are scaled similarly. So we're going to start a little to the left at negative pi over 2. And then I'm going to have to do this a little more carefully. Pi over 2. Then this would be pi. And this would be about 3 pi over 2. So our heights of 1 and negative 1. And in blue, I'll do y equals cosine of x. I saw this cosecant, I thought I messed up for a second. So we're going to do y equals cosine. Now we know at 0, the height was 1, then it goes to 0, then it goes to negative 1, then it goes back to 0. Now at pi, it would be positive 1, but I said I'm not going to include that in the waveform because it makes it a little ugly. But the negative pi over 2 would also be 0. So the cosine wave, now when I'm drawing the cosine wave, it looks like a sine wave, doesn't it? The reason it now looks like a sine wave, you can see my scaling is a little off in terms of horizontal distances. Sorry about that, but that's okay. It's actually more about the vertical distance. That's why I want to clean that up. Raise the negative 1. Let's just put that a little lower. There we go. That's better. About there. There we go. All right. So again, previously we didn't do this section for a cosine. We started here and then we would end here at 2 pi. But I've said, because we know ahead of time, we the teachers, not the students, we know that if we drew a secant graph from here, the asymptotes are going to make it look really weird. So somebody decided, hey, let's do the cosine wave in this orientation, starting at negative pi over 2 until 3 pi over 2, because that'll make the asymptote set up a lot better. So we know there's asymptotes at every location where it's 0. There's a 0 here, here, and here, which means the reciprocal function has asymptotes at those 3 points. So asymptote, asymptote, asymptote. So in black, I'm going to be doing y equals secant of x. So we draw points at the peaks and valleys. We draw amplitudes wherever the reciprocal function was 0, and then we just make those, quote, parabola-like shapes in between the asymptotes. The basic reasoning as to why these go the opposite direction, remember, these are reciprocal functions. When you divide by bigger numbers, it makes the answer smaller. That's what the black one is doing. The black one is taking the blue values, dividing by them. So as the blue value gets really close to 0, when you divide by, say, 1,000, or sorry, 1/1000th, you would get 1,000, which is why this black value would be really big, positive or negative direction. So this is our cosecant graph. Now, again, in terms of your homework, in terms of the testing question for these are multiple choice. So you just got to know how these are going to appear. It's a little too simple. I will go ahead and admit that the sines and cosine graphs for the point of this course are significantly more important and will have a much higher focus for us. You will not see me come back to the secant and cosecant graphs very often after this section is done. On the test, I might throw one question from this entire section of secants, cosecants, tangents, and cotangents. So again, I'm being very, very transparent here. I put a heavier emphasis on the stuff that gets used a lot more. Now, again, I'm not saying this stuff isn't ever used. When you go to calculus, these ideas are important. When you start doing calculus formulas with these trigonometric equations, you have to understand where they're undefined. You have to understand where they're increasing and decreasing. All right, so I want to go ahead and get all the talk done before the examples. So next we're going to talk about tangents and cotangents. So tangent of x, t, and cotangent of x have the same a, b, and c, but period is instead of 2 pi over b, it's simply pi over b. This is because, well, we've already said this, sines and cosines have a period of 2 pi, whereas tangent has a period of pi. We talked about how when you look at that unit circle, because of doing the ratio instead of just the singular coordinates, that pattern starts repeating itself in half the amount of time. Like the sine goes 0, 1, 0, -1 when you go full 360 degrees. Tangent goes 0, undefined, 0, undefined. So it does the same thing twice as fast. 0, undefined, you can just go ahead and say that it repeats itself after 180 degrees. This is where people will mess things up. It's a constant issue, whether it's graphing or whether it's analyzing another situation from before or in the future. The fact that tangent has half the period. The adding stuff is the same because you take the period and divide it by 4. So that's the same idea. So because the A's and B's and C's are the same, the phase shift is the same. It's just the period that has a small effect. All right, tangent and cotangent also have vertical asymptotes. Tangent, stop uppercasing things word, has vertical asymptotes at pi over 2 plus n pi. You want to know why? Silly word. Stop changing my upper and lower cases. Tangent has the exact same vertical asymptotes as secant, because secant has cosine in the bottom and tangent has cosine in the bottom. So tangent has the exact same vertical asymptotes as secant because both of those have cosines in the bottom. Secant is 1 over cosine. Tangent is sine over cosine. And we don't care about the tops for doing vertical asymptotes. We only care when the bottom is 0. So tangent has those as their vertical asymptotes, and cotangent of x as vertical asymptotes of, well, let's see if we can figure this out. Cotangent's cosine over sine. Sine was the reciprocal of cosecant. Cosecant had vertical asymptotes of multiples of n pi. So it should be the same as that, n pi. I'm not going to show all the justification for that again. I do as much as I can with the little time we have. Okay. So when we were graphing the secants and cosecants, we said to draw the sine or cosine wave and then do little parabola-like shapes from the peaks or valleys. Not quite the same for tangent and cotangent, unfortunately. Tangent and cotangent. Actually, I want to say this separately. Tangent looks like several cubic functions between vertical asymptotes, whereas cotangent looks like several negative cubics between vertical asymptotes. Here's the reasoning. If you were to do a very, very, very short, very, very, very short table of values, how do I want to say this? For tangent, what you end up doing for one wave, so a period of pi means you're going from 0 to pi, but again, it's in trying to make the vertical asymptotes make a prettier looking graph, we go from negative pi over 2 up to pi over 2. But we go negative pi over 2, and for reasons, then we do negative pi over 4. I wrote negative twice there, excuse me. Then we go 0, pi over 4, and then pi over 2. So for tangent of 0, the middle one, we're going to look at the quadrantal. Tangent of 0 is the ratio of the y over the x. Y is 0, x is 1, 0 over 1 is 0. So the tangent of 0 is 0. The pi over 2 and the negative pi over 2, those are also quadrantals, so we'll go to the positive 90 and negative 90. Positive 90 degrees is up here. The y over the x is 1 over 0, but 1 over 0 is undefined. Also here at 270, which is negative 90 degrees, negative 1 over 0 is also undefined. So these are undefined, undefined. We really like to have undefineds for anything that has asymptotes be the anchors. See, for the cosecant, we liked undefineds for the first and the last. For the cosecant, we liked undefineds for the first and the last. So that's kind of what we've done here to make that happen. We go from negative pi over 2 to pi over 2. The negative pi over 4, we're just going to use the reference triangles. So pi over 4 is 45 degrees. Tangent of 45 is 1 over 1. So the tangent of 45 is 1. So this is a positive 1 here. That's positive 45 degrees. Negative 45 degrees, though, puts us in quadrant 4. Tangent's negative in quadrant 4, which makes that a negative 1. So when we go to do our graph of this, let's do it here. Is that going to be good enough? Yeah, that'll be good enough. X, Y. I'm only going to go pi over 4, pi over 2, spacing equally negative pi over 4, negative pi over 2. Then I have a height of 1 and negative 1 that I need to illustrate. 1, negative 1. But when I go to graph these points, we have that origin is a point, that's the middle one. The first and the fifth were the undefined at negative pi over 2 and pi over 2. I need to scroll down just a touch, just a touch. Here we go. The negative pi over 4 has a height of -1, which is right here. The pi over 4 has a height of 1, which is right here. Now it looks like a straight line, but we know these are curves. Asymptotes denote bending. Trig functions denote bending. So let's bend. And I even gave you a hint. It looks like several cubic functions. So we're just drawing the one. So this is what I mean by a cubic. It has that kind of bendy cubic shape, but the asymptote means it can't keep going right forever. And then the same thing, but in the downward direction on the left. That got a little ugly. Let's try again. There we go. And it should hug the asymptotes a little quicker than what I've illustrated, but not bad for by hand on a tablet I'm flying blind with. So this was the graph of y equals tangent of x. Put that here. It's a very different process. All three, sine and cosine have their own process. Secant and cosecant have their own process. Tangent and cotangent have their own process. All right. So because we like to have these things sandwiched between the asymptotes, and again, if you kept drawing this, what you'd have is another one, vertical asymptote, and then another one, and a vertical asymptote. And you can do one to the left, and that's going to go away as soon as I lift my pen because I drew off my border. But again, it's just, it looks like a bunch of cubics, a bunch of positive cubics specifically. Oops. So now let's do the cotangent. Now, if you do the same set of x values, the first and the last here are not asymptotes anymore because you're flipping it. It's going to be your zeros. Basically, everything here is kind of flip-flopped. So where this is 0, cotangent's undefined. Where this is undefined, cotangent is 0. So we don't want to have the vertical asymptote in the middle. It would make the cotangent ugly. So we actually go back to a more traditional 0 up to pi. So 0, then pi over 4, pi over 2, 3 pi over 4, and then pi. We're just reciprocating these values, really. So for 0, reciprocating that is undefined. At pi over 4, it was 1, so now it's still 1. The negative pi over 4 is the same thing as 3 pi over 4 due to the periodic nature of things. So this would be the -1. Why did I write undefined here? That was on me. I'm sorry. Not undefined there. The ones were correct. The ones in the negative ones were correct. It's that 0, cotangent of 0 is undefined. If you don't trust me, cotangent in terms of coordinates, remember tangent is y over x, so cotangent x over y. Go back to our unit circle. So again, we're going x over y. So at 0, x over y is 1 divided by 0. That's undefined. So at 0, that's undefined. Pi is the same thing as 0 with periodic nature, so that's undefined. So the cotangent of pi over 2 should be flipping the tangent of pi over 2. Here's the tangent of pi over 2. I looked at the 0 on accident. That was on me again. It was undefined here, which means it's 0 here. We're flipping undefined, which is 0. If you don't trust me, cotangent of pi over 2, that's 90 degrees. So we're using the x over y once again. We're going to be on the unit circle though. We're on 90 degrees. 0 over 1, 0 divided by 1 is 0. Again, the order of doing x over y or y over x depends on tangent or cotangent. All right, so our graph, just doing one quote waveform. So we got, let's go to pi over 2 here. Should put pi about here. It's the pi over 4 here. 3 pi over 4 here. We know we have our vertical asymptotes on the ends. Ooh, that was terrible. One more undo, there we go. There we go. Then our points. So pi over 4 has a height of 1. Should actually label the heights right. 1, -1. So pi over 4 had a height of 1. Red though, red. Pi over 2 had a height of 0. 3 pi over 4 had a height of -1. Do not draw a straight line, draw curves, make them bend, and you end up with that negative cubic looking thing. How can I tell whether it's a positive or a negative cubic? Positive cubics go up and right, down and left. Negative go left and up and right and down. That was something you should have studied extensively in Math 161, and your teacher, if you had me, told you to never forget it. Because those simple base ideas get used in extended concepts, and it's helpful to remember. There are a lot more details and things to be careful with this. Did I say to memorize this and memorize this? No, I put these together one piece at a time, which is the type of thing you're expected to be able to do when you're calculus students, and you're going to be using pieces of this puzzle in a bigger concept. Your calculus teacher isn't going to say graph tangent of X. They're going to say to understand some properties of it to rationalize something in a bigger picture. So understanding the asymptotes, understanding that you want to split the window in this manner versus this manner. Same thing for the secant versus the cosecant. Our starting area for cosecant was at 0, but it's cosecant, I'm sorry, for secant, the weirdest one in my opinion was this one. I was looking at cosecant, which is why I said that, because these are over here. How are we on time? 10 minutes. All right, so let's re-eyeball the secant cosecant stuff, because nope, never mind. The first one I'm gonna do is tangent. Since we just did it, let's stay with what we just did. I'm gonna retrace my steps. So these are your tangents and cotangents. I never actually wrote the part here, but this was y equals cot x. And again, these go on forever and ever and ever, so that while the tangent graph is a series of these separated by asymptotes. So that was a bunch of tangents, waves. The cotangents would be a bunch of those separated by asymptotes. And when you look at a bunch of them, you can see why you want to have the window in that specific order. So if you instead went from -pi/2 to pi/2, it's only this that you'd be looking at. So you'd have the downside here, the asymptote, and then the upside there. This almost looks like a graph of a rational function. Kind of funny that it relates to it. But it's not a very accurate depiction of how it's actually growing and moving because of this discontinuity with the part that is continuous. So again, that's the logic and reasoning why we separate them in such different ways. I know it's annoying. I know it's frustrating. I've been there. But that's why we say it's important to understand where these things are undefined. Where these goofier functions are undefined tends to tell you where to start your graph. All right, example 1, finally. I can never spell it. Graph. And it's just example 1. So it's going to be y equals 2 tangent of 6x. Same thing as sines, cosines. Identify the a's, b's, and c's. Whether the a really makes sense in an amplitude concept anymore doesn't matter. It still governs that point. So those points that were 1s and -1s, because that's a 2, those will now be 2s and -2s. So our A is equal to 2, our B is equal to 6, and our C is 0. There is no plus or minus a number. So that says the amplitude, and I like to put this in quotes because it's kind of not an amplitude, but still important, is 2. The period, so remember tangent has a period of pi traditionally, but now it's pi over b, so pi over 6. And there is no shift. And then the adding number is the period over 4, which is pi over 6 over 4, which is pi over 6 times, that's dividing by 4 over 1, so that's the same as multiplying by 1 over 4, which is pi over 24. Now notice I said add. I want to put a little asterisk here. It's and subtract, in fact, because this is one of the graphs that you just don't keep moving right. You don't start at 0 and keep moving right. You got to go right a couple points and you got to go left a couple points. Now the asymptote calculations, it's more of a pain in the butt to just generalize them in this format, so we'll just see them come out as undefined and it'll tell us. So for our table of values, x and then y, which is the 2 tangent of 6x, we're going to have a first point, a second point, third point, fourth point, and a fifth point. The middle one is 0 because there was no shift. Then we'll keep adding pi over 24 to get the fourth and fifth one. So 0 plus pi over 24 is pi over 24. And then if you add pi over 24 again, you'll get 2 pi over 24, which is pi over 12. I'm expecting you to be able to handle that fraction arithmetic on your own at this point. If you're not, you need to do what? Practice. Remember, 6 hours a week on top of the 3 hours for class. That's 9 hours a week of your life that you're dedicating to this course. 3 in, 6 out, maybe more if you're still having trouble. Now going left, if you subtract pi over 24, you get negative pi over 24. You do it again, well, the symmetry says you're going to get negative pi over 12. We know we are designing these so that the undefined is the anchors. If you don't trust that, what you can do is show a little bit of work. So plugging in the first, you would get y equals 2 times the tangent of 6 times negative pi over 12, which is 2 times the tangent of negative pi over 2, which is negative 90 degrees. So we go to our unit circle, negative 90 degrees, negative 90 degrees, which is here. Tangent's the ratio of y over x. So it's negative 1 over 0, excuse me, which is undefined. You can plug in the fifth one if you'd like to prove that it's undefined, but I'm just going to use the pattern. The middle one should be 0. Yeah, so I won't show the work, but I'll talk it through. If you plug in 0 here, this is 0. 6 times 0 is 0. The tangent of 0 degrees, going back to the unit circle, here's your 0 degrees. Tangent is y over x. 0 over 1 is certainly 0. Oops, too much. Undo. There we go. So 0. I will show the second. You can do your argument of symmetry to figure out the fourth, or show the work if you have to. Y equals 2 times the tangent of 6 times negative pi over 24, which is 2 times the tangent of negative pi over 4 when you reduce it. That's negative 45 degrees. And we already talked about how the tangent of 45 degrees is 1, but it's negative 1 in quadrant 4. So that's 2 times negative 1, which is negative 2. So that's a negative 2. Symmetry arguments, you can probably make that that's a 2. You can show the work if you have to. So I talked the work out for the middle one. I used symmetry and patterns for the fourth and fifth. You do you, though. So that gives us the ability to make our graph. And this will be the very last thing we do. So we have our table of values. Nice, more vertical graph, because tangents, sines and cosines are the ones that you need more horizontal. The rest are more vertical. So we need to go up to heights of 2 at least. And negative 2. Our x values are very annoying. I know, but that's life, right? So this is our negative pi over 12, our negative pi over 24. Spacing even, pi over 24, pi over 12, and then our heights, we'll do in orange. The middle one was 0, the first and third were undefined, because we're only doing one wave. I know it doesn't look like a wave, but we do still call it a wave. It's just a non-traditional shape of a wave. Then the heights of negative 2 on the left one, positive 2 on the right one. Don't draw a line, make it look like that cubic shape. So bendy, 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 getting closer towards the asymptotes. that was not good. Third tries the charm, right? There we go. Much better. So that is our graph. 2 times the tangent of 6x. Now, sure, light isn't traveling like that. Sound isn't traveling like that. But we can definitely mimic some electronic signals using a tangent function. There are definitely aspects of mechanics in the real world that follow this kind of pattern. So don't discount it just because it doesn't look like a traditional wave. All right, so when we come back, we'll do 2 more of these problems. There'll be a secant and a cosecant problem specifically, and in that order, actually. But then we'll call it a day on that section. As a reminder, this section is not going to be heavily emphasized for the rest of the course. You will have up to 1 question on the test involving these. But I do say you could have up to 1, so you have to understand them. But at the same time, I'm also saying there's only 1 question. If I did a 20-question test, that would be 5 points probably. You know, maybe this is the section you studied last, because at most you'll miss 5 points if it was a 20-question test. Whereas, you know, the last section of this chapter, I'll probably have like 5 or 6 questions on, so not studying that section could hurt you like 30 points. Just to give you, you know, a level of importance, I suppose.
Obviously, ignore the next class part. We're going to still continue that right now. Just setting up. All right, here we go.
Leaving off where we had in 5.6. So 5.5 was sine and cosine graphs, the waves, the more traditional waves, like the blue thing you see right here. That's a sine wave. Or this, or the blue one you see here is a cosine wave, but shifted 90 degrees to the left. Because normally you start here and then keep going until you hit 1 again at 2 pi. We said that whenever we want to graph the reciprocal functions of sine and cosine, what we do is we draw the sine or cosine wave, and then we just draw parabola-looking shapes from those, but they'll be sandwiched between 2 asymptotes, and the asymptotes are wherever the original function was 0, because the inverse trigs mean you're taking a reciprocal of 0. 1 divided by 0 is undefined. So that was why these cosecant and secant graphs have all these asymptotes, because sines and cosines have all those zeros, which means flipping them means a bunch of asymptotes, a bunch of undefined values. So we did the graph of cosecant by flipping sine. We did the graph of secant when I say flipping, I mean metaphorically speaking, I suppose, by flipping the cosine. But we said that because it would look really ugly, if I had originally taken this thing up to 2 pi, so there's 2 pi, that means that the secant graph would have looked like this. You'd be cutting off this part right here. You'd be completely ignoring all of that section, and you would have this, I'm drawing what you'd see in red, and then this, and then this, which looks like 3 different pieces, which is why we don't do it that way. We just said, hey, let's just draw it from negative pi over 2 to 3 pi over 2 instead. That's still 1 period. That's still 360 degrees worth of x values there. But then you only have just 2 looking parabolas, 1 up, 1 down. We didn't have to worry about the sliding around with this one because they naturally happen, and put the asymptotes in good places. Then we did the tangent and cotangent. The first thing we had to make special note of is that tangent and cotangent have a period of pi over b, or pi if there's no other modifiers there, whereas everything else was 2 pi or 2 pi over b. They have the same asymptotes because tangent has a cosine in the bottom, so where we're cosine 0, which are the multiples of pi over 2 and adding pi, you'll have your asymptotes. And then cotangent has sine in the bottom, and wherever sine is 0, this will have asymptotes which are literally just at multiples of pi. So we had all of those great details in there. And we said that these graphs end up looking like cubics sandwiched between asymptotes. And the tangent had the same issue as the secant graph, where if you went from 0 to pi, you'd have half of it going up and then half of it going down, separated by an asymptote, and it would just look weird. So he said, so we can make it one graph looking thing in one waveform. Let's just sandwich it between two asymptotes here and here. Then cotangent didn't have that issue. You were able just to go from 0 to pi. It's funny how some have the issue and some don't. And it always seems like one in each of the families has an issue and the other doesn't. And then we graphed 2 tangent of 6x. And you can see all the work. I'm not going to reiterate that. Look at last lecture for that detailed work, because now we're going to go straight into example 2. It'll be to graph y equals the secant of 2x. Still a good idea to identify your a's, b's, and c's like I did last time. So for this, there is no a written, so it has to be 1. There is a value in front of the x. Sorry, I'm looking at x, so I was about to write it, and that's a 2. There is no plus or minus number, so there is no c, which means there'll be no shift. Your c is 0. I'm just trying to keep things organized in the same way. Okay, good. So therefore, our amplitude, and again, I put it in air quotes. I say air quotes, but I'm not doing this in front of you. I put it in quotations because it's not a true idea of an amplitude. It's not a peak, but it at least does give us an idea of something. So that's related to the a, which is not the 2, that's the 1. Then the period should be the pi over b, which in this instance is going to be 2 pi. I said pi, didn't I? I meant to say 2 pi. This is secant, so 2 pi over the b, which was 2, making it pi. I had the answer in my head, which is why I said pi initially. And then there was no shift. All right. The only thing we have left to figure out is what we're going to add over and over and over. So where we take the period, which is pi, and divide it by 4. And there's no reduction to do there nicely. Now I say add, and then in the problem for the tangent, we also had to subtract. So I just like to make a little memo that maybe you have to subtract it as well. So a secant graph, that was flipping the cosine, right? So secant graph, that was flipping the cosine. So here was the cosine wave, and that was one that we did have to shift over a little bit, that kind of annoying negative pi over 2 aspect. So you would have had to have accounted for that as well here. But you don't just start it at negative pi over 2. You're going to have that issue where you've got to add and subtract the pi over 4. So that number is not going to just be pi over 2, negative pi over 2, that is to say. This pi over 4 dictates it. So I say maybe subtract, but you are definitely for this problem. I just don't want to leave that permanently up there. All right, so our second point, that's going to be 0. Our second point is going to be 0. Notice I didn't start at the first one. I started with the second one. And that's, again, I'm going to scroll back up to the reasoning. Oops, too far. There it is. This is the type of graph we're going to make. We're graphing a secant, a variation of a secant, secant of 2x. So we can't just start at 0. We have to subtract once to get the left point. Then we'll go back to 0 and add 1, 2, 3 times to get the other points. It's a very weird setup, I know. So the first point would be the previous one, 0, but then we're going to subtract that adding number, which is pi over 4, which would give us negative pi over 4. Then the third x value, we take the second one, 0, because if you take the first one and add pi over 4, you'll get to the second. And then we add the pi over 4, which will give us pi over 4. The fourth point, we take the previous one, which is pi over 4. Whew. I was trying to get to the mute button for that. Sorry, excuse me. Oh man. Give me about 15 seconds. I need to go get a tissue. All right, I'm back. All right, so that just looked a little. No, I hit erase. Erase for the third time. I'm just making that pi a little prettier. So we take that original, the third point, and we add the adding number of the pi over 4, which pi, 1 plus 1 is 2. That's 2 pi over 4, which reduces to pi over 2, of course. And then finally, our fifth point would be the previous one of pi over 2, but I'm going to use the non-reduced version. We talked about that last time, how it's just better to go ahead and do that, otherwise you're going to get the LCD anyways. So 2 pi over 4, then add the adding number, pi over 4, and that'll give you 3 pi over 4. Now, if you remember that little trick I gave you, it said that if you took the first point, which was the negative pi over 4, if you added the period of pi, which is 4 pi over 4, negative 1 plus 4 is 3, you do get the fifth point. So everything lines up perfectly. Again, if you think you're supposed to start at 0 and then go to pi, I mean, you'll have 5 accurate points of the graph, but it will not be the waveform that I would want. Now, again, in my math lab homework, that's not an issue. In the test, because I'm going to be doing that in my math lab, it's not actually an issue. I have said that I might ask you to do by hand, you know, all of this detailed stuff for me to see and then just draw up the one waveform. I will be honest, I'm not going to have you do it with the secant, cosecant tangents, or cotangents. For the secant, cosecant, tangent, or cotangent, if I throw one on the test, it will be like in my math lab homeworks. And that's because we're not going to be using this as much throughout the semester, whereas the sines and cosines we will circle back to, pun intended. All right, so we can start drawing our table of values in a better way than that, please. So x, y, all we've got so far are the x values of negative pi over 4, 0, pi over 4, pi over 2, and 3 pi over 4. And the y values we're supposed to get by doing all that flipping and stuff. Now, you can go straight to these if you remember that the first and the fifth are supposed to be the undefined. So we can say, hey, what's that secant graph look like? Yeah, the first, the third, and the fifth are supposed to be undefined because the cosine graph had zeros at the first, the third, and the fifth when it was adjusted to make it look more like a sine wave. Again, that's weird feature 1. So it's undefined on the first, third, and fifth. You can do the work to confirm that if you like, but I'm not going to do it this time. If you plug those in, you will end up getting undefined answers. I'll show it for the first one first. So that was the secant of 2 times negative pi over 4, which is the secant of pi over 4, which would be 1 over cosine of negative pi over 4, by the way. That is a negative still. So 1 over cosine of negative pi over 4. Well, cosine of pi over 4 is square root of 2, hold on, pi over 4. Four? No, 2. What? I knew something looked wrong. I keep looking at the pi over 4s over here. 2 and the 4 reduced to a 2. There we go. So that's the secant of negative pi over 2, which would be 1 over the cosine of negative pi over 2. When I wasn't going to quadrantals, that was my red flag. It's like, no, they should only be quadrantals. So cosine of negative pi over 2. I didn't pull up my cheat sheet. Remember, this is stuff you're supposed to know. But at negative pi over 2, we're down here. The x value is 0. Cosine takes the x value. So that's 1 over 0, which is undefined. Third and the fifth will follow suit. If you don't trust that the second one is going to be the amplitude of 1 or negative 1, I'll show the algebra for this one, but not the rest. So the secant of 2 times 0, which is just the secant of 0, which is 1 over the cosine of 0. Well, unit circle again. Unit circle again. Here's 0. Cosine is 1. So that's 1 over 1, which is 1. So at 0, it's 1. At pi over 2, that means it would be the negative 1. So then we can draw our, quote, wave. X, y. We got x values of negative pi over 4, 0, pi over 4, pi over 2, and 3 pi over 4. So in blue, I'm going to draw the actual cosine wave. Now, the cosine wave, we traditionally start at 0, at x equals 0 with a height of 1. I got to put my heights up here as well. 1, negative 1. So this would be the cosine, and then here, and then here, and then here, and then we'd complete a v. Here would be 2 pi, but because we're drawing a reciprocal function, we know it's a little weirder. That's why we went to the left one. So then we make our nice little wave. It looks more like a sine wave now. That's okay. So that would be, in the blue, that's y equals the cosine of 2x. To draw the reciprocal function, we make asymptotes wherever the original is 0, because we're flipping it. 1 divided by 0 is undefined. And then we draw those little, so in black will be the actual function, y equals secant of 2x. So you have the same heights on the peaks and valleys, and then you just draw little parabola-like shapes inside the asymptotes from there, going up and down appropriately. The bottom one should look a little more like the top one. I just ran out of room. I can't draw through this little section right here because Word is not perfect. That would be Word perfect. Sorry, cheesy joke that probably most people don't even get because who uses Word perfect anymore? All right. One more for the road. For the section. Example 3 graph, we're going to do y equals 2 cosecant of x. So when we're drawing a cosecant, that means we need to flip a sine graph. Now, sine didn't have the weird issue of having to move it a little left. Now, the cool thing is, if you remember what these images are supposed to look like, if you tried to do this previous one from 0 up to pi, so you wouldn't have drawn this segment, and instead you would have finished the wave here, which meant you would have had your actual secant function look like that. When you drew one waveform that went like this, and then this, and then this, having those 3 different looking sections, that's where you should go, wait a minute, that doesn't look like just parabolas being separated by asymptotes. It looks like I've got several different ones separated by asymptotes. So you go, oh wait, no, Mr. Beckner said that's when you gotta shift it left. So all right, from 0, let me just subtract the pi over 4 and then draw the parabola like that. That's a good way to correct that. Okay. All right, so the amplitude A, well, A, not the amplitude yet, is 2. The B is 1 and the C is 0. I don't like doing these with shifts, honestly, for y'all as intro examples. Makes things way worse. So the amplitude in quotes is 2. The period, this is not a tangent or cotangent, so it's 2 pi over b. So 2 pi over 1 is 2 pi. There is no shift. And then the thing that we have to add over and over is the period divided by 4. 2 pi divided by 4 is pi over 2. All right, so the first x value. Now I know that this one, since we literally just did a secant and it had that weird, you got to move left issue. The other one doesn't, cosecant doesn't. We will be able to start at 0 and go all the way up to 2 pi. So the first x value is 0. The second, we take that one and we add pi over 2, which is pi over 2. To get the third, we take that pi over 2 and we add pi over 2 again. We just keep adding pi over 2. Pi over 2 plus pi over 2 is pi. It's 2 pi over 2, which is pi. I'm not going to show that reduction. The fourth one, we take that pi and we add pi over 2. And I skipped showing the reduction for a reason because I know you might do it. But then that means here you'll have to get an LCD. If I had showed it before reduction, I could at least borrow the information. But I did say it at least. Pi is the same as 2 pi over 2. Then when you're adding your pi over 2, you get 3 pi over 2. These are really familiar sounding numbers. And then finally the fifth one, the fifth x value, we take the 3 pi over 2, we add the adding value of pi over 2, which will give us 4 pi over 2, which is 2 pi. These are actually the 5 basic x values when we just do a standard graph, and that's because the b was a 1. When the b is 1 and there's no shift, these x values always end up being quadrantals. The amplitude being 2 will have an effect though. So what's our table of values looking like so far? X, Y. The first one we got 0, then the second one's pi over 2, then pi is our third. 3 pi over 2 is our fourth, and then 2 pi is our fifth. Well, we know the first, third, and fifth are going to be the undefineds. If you don't trust me, go ahead and draw up what we were doing a cosecant, right? Yeah, cosecant, so we're going to drop the sine wave. And with these x values of pi over 4, pi over 2, excuse me, pi, 3 pi over 2, and 2 pi, we know that the cosine was going to look, excuse me, sine, 1, 2, 1, 2. We know that the cosine graph, I keep saying that. We know that the sine graph was going to have these as their points. Those are the ones you better know inside and out. So we're supposed to graph a cosecant, which means we flip the sine graph. So what this is y equals 2 sine of x, not just sine, 2 sine of x, which is why these points are at 2 and negative 2. And then you get your nice, pretty sine wave with heights of 2 and negative 2 for the peaks and valleys. But then what we do is we draw asymptotes wherever this was 0, which is right in the center of our single wave, and then on the ends. And then we draw little quadratics stemming from those. So that's what the graph should be. So we know this is undefined, undefined, undefined. The first one ends up being the original amplitude. I will show the work for that. That's y equals 2 cosecant of pi over 2, which is 2 over the sine of pi over 2. Sine of pi over 2 is 1, so that's 2 over 1, which is 2. You can look at the unit circle and confirm that at 90 degrees, the y value is positive 1. And that makes this one negative 2. And there we go. There's our graph. So in black, is y equals 2 cosecant of x. So these aren't terrible when you have multiple choices you're looking at and you know the idea of how this is done, but it is a much more convoluted problem than just doing a sine or cosine graph because, well, you got to do a sine or a cosine graph just to start the thing and then know how these things are growing from there. And we did lightly describe the reasons they look like this because as the sine number is getting smaller, the reciprocal function should be getting bigger. The closer you get to 0, in the one function, the reciprocal is getting closer to infinity. So it starts growing really, really, really fast. Okay. So that will close out 5.6. .7. Inverse trig functions. This to this, enter, left. Lots of enters, lots of space. There we go. Inverse trig functions. So back in Math 161, back in pre-calculus, 163, wherever you had it, whatever number it was called, you were supposed to study inverse functions in that class. And inverse functions, I always liken to Jeopardy. It's where you have the answer and you're wondering what the question was. That's the concept of inverse trig function, of just inverse functions in general. You have the answer and you're wondering what the question is. And in mathematics, this is very often a much more complicated type of problem. In fact, you've all done an inverse problem before you even got to pre-calculus, square roots. The square root of 100 is 10 because 10 times 10 is 100. And it's like you got the answer to something being squared equals 100. And you're trying to figure out what was the question. What squared equals 100? So the square root is our first inverse problem. And in math, this inverse problem can get very, 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 very crazy, but we're not really there yet. So the idea of functions being invertible, first of all, is that it had to pass the horizontal line test. So this is Math 161 or pre-calc 1, whatever you want to call it, to have an inverse function. The original function must pass the horizontal line test. And you might be thinking, Mr. Beckner, don't you mean the vertical line test? No, I don't. The vertical line test is to tell if something's a function, which if I'm saying it's originally a function and we're trying to find its inverse, it passes the vertical line test. The reason the inverse idea has a horizontal line test is because what you do to get an inverse function is you change x and y coordinates completely. Left becomes down, right becomes up. So when you take a function and you do this, when your left and right become up and down and vice versa, now in order for that thing to pass a vertical line test, before you changed from one thing to another, those would have been horizontal lines because everything we called left and right before is now up and down, and everything that we called up and down before is now left and right. So that's why this is a horizontal line test. A horizontal line test on a regular function shows that if you do flip everything around, that it would still be a function because then it would pass the vertical line test. All right, so horizontal line test means you can draw a line anywhere and it goes to the function only once at most. Actually, I want to bold that whole thing. Once at most. So 0 is okay, once is okay, but not 2. Due to this, we're going to say, see below, y equals sine of x, stop uppercasing things, must be restricted to a domain of d equals, and then between brackets, there we go. Maybe a little more space than that probably, there we go, is going to be negative pi over 2 pi over 2 in order to be invertible. We have to restrict the domain of a sine function to negative pi over 2 and pi over 2. So the furthest left we're going to go is negative pi over 2. The furthest right we're going to go is pi over 2. You might be thinking, Mr. Beckner, that seems weird. We're going with the idea that sines, when we graph one wave, we go from 0 to 2 pi. Yes, when we're graphing waves, when we're graphing a sine, you go from 0 to 2 pi if there's no a, b, or c written. When we're talking about these inverse functions, this is the window we would need to be thinking about. So here's why. And I'm actually going to do this on like a whole page lower. I want to leave some space here. How much space do I need? That'd be fine up to about there. I think this will do it. So the reasoning below. Here's the graph of y equals sine of x. Now this graph goes forever and ever and ever and ever and ever in each direction. Starts at 0, goes up to a height of 1, comes back down a height of -1, then back up, etc., 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 etc. It goes on forever and ever and ever. So this graph right here, if I drew a horizontal line way up here, it's fine. That doesn't even touch it at all. But if you draw it anywhere in this window, look at how many times 1, 2, 3, 4, 5, 6, and that's only what I've illustrated. This thing goes on forever and ever to the right, so this wave crosses that horizontal line infinitely many times. This is not invertible. So we restrict it. And you're going to see me just try and restrict this in a couple different ways. The first thing some people think is, well, let's just go from 0 to 2 pi. You just go from 0 to 2 pi. Well, look, you still fail once, twice, even down here. Once, twice. So that wouldn't work. So you can't just go from 0 to 2 pi. So the first instinct a lot of students have is, well, let's just half it. Let's, instead of going from 0 to 2 pi, let's go from 0 to pi. And if I go from 0 to pi, that's not it. It looks like this. And this, guess what, still fails. It's not invertible. So in fact, that right side of the wave, the furthest that you can go up to is pi over 2. Because the second you go past pi over 2, if I go just a little bit lower, now I'm going to fail the horizontal line test. So that's the right-sided restriction. And you go, okay, well, let's just go from 0 to pi over 2. No. Remember, we wanted to try and have as much as possible for our domain of a restricted function. And we did this for x squared back in Math 161, if you had me. Where we only had to cut off the left half of it, but now we got to cut off a lot. So we got from 0 to 2 pi. Well, maybe we could go left. Well, we know that the left side of the wave would do this if we kept going, but I've gone too far. That would fail the test. So what I got to do is stop when I hit the lowest point. I got to stop right here, which would be at, guess what, negative pi over 2. That right side looks just a little ugly. Just make it a little prettier. Here we go. So in terms of an invertible function for sine, just for sine, that's all we can look at. That is going from negative pi over 2 to pi over 2. This is invertible because any horizontal line you draw will only touch it one time. So that's why we did this. Y equals sine of x must be restricted to a domain of negative pi over 2 to pi over 2, and those are brackets, which means they are included. Okay, so back up top. So we have notation, and I'm going to have to write in pen for this, or it's going to take me forever. So y equals sine of x, that's the normal trig function we've been dealing with so far. Y equals, and the way we read this is not sine to the negative first power. This is inverse sine of x. This is what I was saying back in 5.2. There were at least 1 or 2 homework problems where you have to use this in your calculator, but it was just a calculator thing and they taught you how to do it. That's why I didn't approach it yet. I didn't want to talk about inverse trig functions then because I knew we were going to do this grand detailed introduction later. I figured 1 or 2 homework problems, people are just going to dust under the rug for now and not worry about it. All right, so this is read as y equals inverse sine or sine inverse of x. So when you do the inverse of a function, everything swaps. X's and Y's swap, which means inputs and outputs swap, which means domains and ranges swap. So this, instead of having that domain from before, we'll have a range, which is the Y values of R equals negative pi over 2 comma pi over 2. The domain of a regular function is the range of an inverse function. The domain of an inverse function is the range of a regular function. They swap. X's of one are the Y's of the other. Y's of one are the X's of the other. Now, before, I didn't write this, but the range for sine of X was from 1 to 1. Why? Because these heights are 1, these heights are negative 1. Even with the restrictions, that highest high is 1 and the lowest low is negative 1. So the range of sine of x between negative 1 and 1 would be the domain of the inverse function. So that's the sine function. In its inverse. So now let's do the cosine. So y equals cosine of x must be restricted. Domain of d equals, and some brackets, some space, close them. And this is going to turn out to be 0 to pi. Of course, it's not the same as sine. Why would it be, right? They always have these subtle differences, and you're not going to figure out and remember these subtle differences without practicing this stuff over and over, without writing notes, without taking notes, reading them over and over, going back to them, highlighting stuff, whatever. So cosine must be restricted to a domain of 0 to pi. Now, I explained why sine had to be restricted, so of course I'm going to do the same for this. So I'm also going to say due to this, which we'll say see below. So we're going to prove that we need to restrict the cosine graph to 0 to pi. So for y equals cosine of x, which originally, when you go forever left and right, heights of 1 and negative 1, we start at 1, and then we're going to go down and then back up and then back down, back up, forever and ever. And the same thing if we were going left, and they'd be a little prettier than what I have, but you get the idea. Clearly, this fails horizontal line test miserably, the same as the sine did without restrictions. So we got to cut this thing down. And the first attempt you might have is, well, let's just go from 0 to 2 pi. So if you go from 0 to 2 pi, we know it starts at a height of 1, goes down, and then back up to a height of 1, eventually like that. but clearly fails, fails. That wasn't a horizontal line, but it fails. It's a little slanted. So 0 to 2 pi is too much. So a lot of times we'll just cut it in half. And then if we think we need to go to the negatives, we will. So instead of going from 0 to 2 pi, what if you chopped off everything over here? Would that be good enough? Well, I don't see anything that looks like it would fail the horizontal line test, so let's try that. Let's just go from 0 to pi. All right, so that's now going to be a pi over here. You can put pi over 2 up here if you like. So cosine starts at a height of 1 here, and by pi over 2, it's going to be here. By pi, it's down at -1. But it's not a straight line. It bends, it waves. That's not the best wave I've ever drawn, is it? A little better than that. There we go. There we go, much better. This appears to pass the horizontal line test. Passes, passes, passes. So we're good. Now, this is good, so 0 to pi works, but it's always worth trying going to left a little. So pi is as far right as we can go, because if I went just a little further right, it starts bending back up, and that's where we start failing the horizontal line test. So you might think, all right, well, last time we were able to go left some. Once we chopped this down to pi over 2, we said, well, what if we can go left? And we were able to. But if we start going left from here, we're doing that. And again, we'd be failing the horizontal line test. So this is actually as much as you can restrict it and remain invertible. How are we on time? 30 minutes. So, same idea, because the cosine is bound with a range of -1 to 1, that means the inverse cosine would have a domain of -1 to 1. And we've already established that since the domain of cosine is from 0 to pi, then it's the range of the inverse function would be that. So y equals, oops, holding my pen upside down, that doesn't help. Y equals cosine inverse of x has a range r equals 0 to pi. And again, that is because the domain of cosine is 0 to pi. And the inverse function has a domain of what the regular function had for range, which is literally the same as the sine, -1 to 1. So the domains of the inverse functions are these values because the regular graphs were stuck between heights of 1 and -1 when we didn't throw amplitude numbers in there. If I threw a 2 or 3 anywhere in here, that would change things in here.
My mic was off and I just realized that. Sorry about that. First I grabbed the wrong class file and then had my mic off. Classic. Okay, so let's say what I just said again. That will be it for the day. We got just a small taste of 5.7. We will do so much more with that section when we come back next class. We'll kind of readdress those intro ideas. I might even just play back a few minutes just to, get used to it since 5 days will have passed and everything. But I wanted us to go ahead and get a small sampling of it. But yeah, so we finished 5.5 and 5.6. They're due in a week. 5.3 and 5.4 are due tonight. Besides that, if you have any questions, you can hit the email. Besides that, have a good weekend, be productive, get some good homework done, and we'll see you Tuesday. Take care, everybody.